Observe this equation. At first glance, it appears manageable. However, the exponent 5 signifies a profound algebraic boundary. This is a quintic equation, and for centuries, it was the final frontier. In 1824, Norwegian mathematician Niels Henrik Abel proved that a general solution in radicals is impossible for the quintic. We have precise algorithmic tools for the quadratic formula, but for the general quintic, such a radical formula cannot exist. The naive impulse is to expand these binomial powers immediately. I remember the frustration of such brute force attempts early in my career. Expansion is a computationally expensive error that yields only noise. True mathematical mastery lies in identifying hidden symmetries. Look at the bases of the powers, x and x plus 1.
Notice that their sum is precisely 2x plus 1.
This is not a coincidence. It is the structural core of the problem. Mapping this to a plus b equals c allows us to bypass the quintic barrier. We must locate the center of symmetry for this problem. Let us analyze the terms x and x plus 1 on the real number line. The interval between them is of length 1. Exactly unity. The most rational reference point is their arithmetic mean, which is exactly x plus 1/2. We define y as x plus 1/2, shifting our origin to the center. Now, inspect the right-hand side, the expression 2x plus 1. It is precisely twice our new variable, y. The structural alignment is undeniable. Observe the transformation as we recenter our coordinates. The variable x is now expressed as y minus 1/2, and x plus 1 becomes y plus 1/2. This substitution uncovers a beautifully balanced structure. Complexity is reduced when we acknowledge the inherent symmetry. This demonstrates the power of choosing an appropriate basis. In mathematics, symmetry is far more than an aesthetic preference. It is a rigorous tool that allows us to collapse algebraic complexity.
By centering our variable at 0, we ensure that terms with even powers of y will negate each other in the final summation.
We apply the binomial theorem to expand both expressions systematically.
In the first expansion, the negative constant term leads to alternating signs throughout the polynomial.
In the second, every term is positive. The underlying structure is identical. Now we perform a vertical summation of these two polynomials. Terms with even powers of y have odd powers of the constant. These additive inverses cancel to 0. Logic halves our complexity. The remaining terms are identical and simply double when summed. We are left with twice the sum of these odd degree components. Simplification yields a clean quintic expression for our left-hand side. On the right, the term 2y to the 5th must be evaluated carefully. This distributes to 32y to the 5th power. The original equation is now reduced to a far more manageable form. We shall now analyze our specific equation using fundamental algebraic axioms with absolute rigor. Our first step is to transpose all terms to the left-hand side to establish a null equality. To eliminate fractional components, we multiply the entire expression by -8. Observe that every coefficient is a multiple of 5. Division by 5 simplifies our arithmetic while strictly preserving the roots of the equation. The absence of a constant term provides a significant structural advantage here. It permits the immediate factorization of the variable y. This yields our primary root, y equals 0. The remaining factor is biquadratic, effectively a quadratic in the variable y squared. By defining a substitute variable u for y squared, we transform the problem into a solvable quadratic form. We now identify the coefficients a, b, and c to employ the standard quadratic formula. Substituting these constants reveals the specific values for our intermediate variable. Rigorous calculation results in two distinct values for our substitute variable. To recover the original variable y, we must extract the square roots of these results. This process identifies two real roots and two purely imaginary solutions. The fundamental theorem of algebra necessitates 5 roots for any quintic equation. We have derived all 5 through logical necessity and structural decomposition. Symmetry is the instrument that resolves what appears at first to be impossible. Recall our transformed roots y and the linear mapping we established earlier. This allows us to map our solutions back to the original variable, x. When y equals 0, x is calculated as 0 minus 1/2, yielding negative 1/2. Substituting 1/2 for y gives us x equals 0. For negative 1/2, x results in negative 1. The real part is shifted by 1/2, while the imaginary component remains fixed. The solution set is now fully determined. 5 distinct roots, exactly as required by the fundamental theorem of algebra. An elegant triumph of structure over brute force. Understanding this order is why I chose mathematics.